coming to you every week.
Welcome to Wireless Wednesdays. I'm going to speak today about why does your wireless control link always suck. So, wireless control links, I am talking not about you texting your buddy a latest fishing video. I'm talking about why does your remote temperature logging system give issues, or a wireless irrigation controller, or a wireless security system, or wireless garage door opener. Why do these things give problems? And there are 5 main reasons what we're going to talk about quickly. The first one is antennas. Do I have an antenna that I can show you? Everyone knows what an antenna looks like. There we go. There's an antenna. Antennas, the point behind an antenna obviously is to get your radio frequency energy from the device onto the air, and from the air back into the receiver. And antennas are sort of a black magic art. Very few people understand it, and they must just work. So, and bad antennas can absolutely spoil your day. So what do we recommend? We recommend that you read the instructions. We read what your manufacturer has specified for the equipment and follow that very, very closely. That's the best way. Don't try and make your own antennas. Don't go and chat GPT. Just don't try and be clever when it comes to antennas. There are a couple of rules of thumb that your manufacturer will typically tell you, and that is, don't install the antenna right next to other things. Keep it sort of on its own. And typically getting it higher up is better. And try and plan your wireless links such that you don't have any unnecessary obstacles between the receiver and the transmitter, as far as you can. Those are the basics. So, antennas. The second one I would like to talk about is transmit power. That is physically how much energy are we actually putting onto the air for the receiver to receive. Now, I like to use the analogy of a husband and wife. I'm married, as you can see. Your transmit power is how loudly does your wife speak and ask you to take out the trash. If she's going to whisper, then you're going to struggle to hear what she's saying, especially if you have a bunch of kids making a noise in the background and you've got the washing machine going guzung, guzung, guzung here in the washing room. She needs to speak up so that you can hear her. So if she doesn't speak up, the message would not come through. And the same goes for your RF links, your wireless issues. Your more transmit power will tend to make your link a little bit more reliable. But the flip side of that is receive sensitivity. It doesn't help my wife is screaming at me to take out the garbage, but I'm not actively listening. So your receiver sensitivity is a measure for how weak a signal can you pick up and make sense of it. Now together, these two together is very powerful because it's a combination of how loudly does your wife speak to you and how sensitive are you to her voice in the midst of all of the noise happening. So that provides us with a signal to noise ratio. So it's not about how loud your wife speaks. It's about how much louder does her voice arrive at your ear relative to all of the noise in the background. So that's the signal to noise ratio. Obviously, if it's dead quiet and no one's making a sound, then she can whisper and you will probably hear her. But if there's a big noise, then you kind of need her to speak up. So receive sensitivity and transmit power and antenna, those 3, and they work very well together. So it follows that if you have problems, it might be that your sensitivity is not good enough. So as far as transmit power and receive sensitivity goes, bumping either of those will increase your link budget, your signal to noise ratio, and therefore the range that you are able to get and the reliability that your link is going to operate with. The fourth one, a fourth reason why wireless links can fail is the dependence on a single frequency. typically, if you look at a device, you'll have a nameplate at the back, and it will say this thing's operating at 433 megahertz, 868 megahertz, 915 megahertz, 2.4 gigahertz, at one of many different frequencies. Now, what happens? It's actually transmitting on that frequency, and it's applying a modulation scheme of sorts on that frequency. So, what is the problem with that? Well, firstly, if any person uses a transmitter somewhere else at that same frequency, then you've got the equivalent of your daughter, whose voice sounds very much like your wife's, speaking at the same time that your wife is speaking to you, and you can't make out what your wife is saying because your daughter is yapping on the phone, you on the side, and her voice is very much the same sort of frequency. So you get a jamming problem where one signal is drowning out the other. And it's especially prevalent if you've got a single frequency. But there's even bigger problem with that than that, and that is what we call multipath fading. So what is a multipath? It's when your signal arrives at the receiver through more than one path. So there's always the direct path between the transmitter and receiver, but that signal might also bounce against some obstacle. It could be a building, it could be a bus, it could be whatever. So the signal is bouncing and it's arriving at the receiver. So now you've got two signals arriving at the receiver. Yes, the bounced one might be a smaller, and it might have traveled further, but they arrive at the same time. Now the problem is, are these signals in phase or out of phase? If they happen to arrive in phase like this, then they're going to add together, and you're going to get a massive signal. It's actually fantastic. Then it's going to have like a lensing effect. But if they happen to arrive out of phase, then they're going to subtract from each other, and you're going to hear nothing. So that's a real issue. That's why sometimes you might find, if you have your antenna right here, you get full signal. It's like working like a charm, and just moving it like a meter this way, boof, all hell breaks loose, and there's nothing. And there appears to be no difference. That's exactly why these things happen. I don't know if you've seen wireless microphones on stage. You'll always see on the receiver they'll have two antennas, and they'll always be like on the corners of the device, so that you've got two antennas receiving at two different locations, and therefore try and get away from this multipath fading problem, because typically your artist that's singing is walking around on stage, so the signal might be bouncing in all sorts of random ways. So that's why they have two antennas. Sometimes they've got even three or four to try and cut down on this multipath fading effect. So a better way to handle this problem is to not rely on a single frequency. What if you transmitted on a bunch of frequencies at the same time? That would solve that problem much more efficiently, and we'll get back to that. So that was the fourth issue. Number 5 is bidirectional communication versus unidirectional. Uni means one, which means, if we go back to our analogy, it's as if your wife is only able to speak and you are only able to listen, and my wife would add, yeah, and then even then it's not always listening that well. Now, no marriage can work this way, and no proper wireless link can work this way either. It takes two to tango. You need to be able to listen, but you need to be able to speak back as well. And it doesn't help that my wife has got a 102 decibel voice. She also needs to be able to listen. We need to be able to have a conversation if this thing is going to work. An example, my wife tells me, go take out the trash, and she's unable to hear. So she can give the command or the instruction or the request, and I can listen, or if it doesn't come through, it doesn't come through. But if I'm able to respond, then we could have a conversation. I could say, sorry, what did you say? And my wife can repeat, and she can see that I didn't respond, and she can say, listen, baby, did you hear me? And I said, sorry, I didn't hear you. And she can say, well, please take out the trash. And I say, sure, no problem, babes. And hopefully I end up doing it. So a conversation is always better than just a one-way hope and pray. In some applications, it can be quite critical. Let's take a security product. This is an example of one. Where do I have I don't have one of the sensors here. Here's actually one of the sensors. This is an early prototype. So the sensor has an antenna, it's got a transmitter. So what happens if it picks up movement, and now it needs to tell the base unit, hey, I've got movement. Older systems would say, we'll send it, and if the base unit doesn't receive it, then it doesn't receive it. End of story. Where it's a security device. It's sort of important that the message comes through. So a much better way is if you've got bidirectional communications, the sensor can transmit the message to the receiver can respond and acknowledge. Now the sensor knows, oh, thank you, my message went through, and it can relax. So it's super important. So as soon as you are able to have a conversation, it just lifts the entire reliability of your entire system by it's just an entire layer of reliability that you didn't have before. So this is super powerful. So the 5 different things is your antennas. It's always your antennas. Transmit power, receive sensitivity. Together, those two make up your link budget, and they determine your signal to noise ratio. And then the dependence on a single frequency and the idea of having bidirectional communications. So when you're having problems, it's almost always a system that is unidirectional. They're almost always dependent on a single frequency. They are not listening well enough, or they're not transmitting loudly enough, and there might be some issue with your antenna. So what do we do at Polygon Technologies? We use LoRa technology. That's what's inside this. This is our Drongo security system. We use wireless sensors, and we use LoRa transmissions. Now, LoRa is an acronym for long range, and it should have been extreme range, because this technology is just amazing. So firstly, it's transmitting at a significant signal. It transmits very loud. Secondly, it's got an amazing sensitivity. Why does it have such amazing sensitivity? It's because of the spread spectrum modulation technology that it's using. So instead of transmitting at 433 megahertz alone, it's actually transmitting across an entire band of frequencies at the same time. So the signal is spread across the spectrum. That's why we call it spread spectrum. So now multipath fading cannot happen as easily, and your signal cannot be jammed as easily. You're going to need a significantly more complicated piece of equipment if you want to jam the signal. And together, all of this gives you absolutely amazing range. With this system, we've tested 60 kilometers of range. Now, who needs 60 kilometers? I mean, that's not practical. Well, mostly these systems, wireless link systems, are always specified in ideal circumstances. They speak of line of sight or open field conditions. So where you're standing in the middle of nowhere with your transmitter here and your receiver some distance away, and the maximum distance that you get, that they call that your open field or your line of sight range. Now that's always going to be way more than what is practically achievable, because practically real life is sort of messy. It's not as simple as just the two seeing each other. Realistically, the signal needs to go through a couple of, like on this case, this base unit might be on your bedside table, and the sensor is outside on the wall somewhere, or down by the chicken coop or somewhere. So the signal needs to travel through walls, through obstacles, through bushes and vegetation and all sorts of things. So real life is messy, and the signal gets degraded when it has to penetrate through all sorts of obstacles. So yes, we might get 30 or 60 kilometers open field, but once you've gone through a bunch of obstacles, that range reduces down. But traditional systems will specify 1,000 meters of range. Now, 1,000 meters of range, I can see applications where you might need that, but that 1,000 is specified at open field line of sight conditions. So in real terms, you're going to get a couple hundred meters if you're lucky. So if you have a massive budget, link budget, in terms of a really good sensitivity, really good antennas, really high transmit power, all of these advantages, then that 60 kilometers of open field range translates to really usable range performance in real world conditions, where your signal needs to go through funny paths to get there. So that's why we use the LoRa technology. It is definitely more expensive, but it's worth it. It's worth it. So we use it in our Drongo technology. This device right here. We also use it we've got a product that allows you to, if you have a float switch inside a tank, you can have that float switch speak to wirelessly via LoRa link to a pump that is located remotely, so that the pump can keep the tank filled up. And we call that remote float. It's using the same kind of technology. We also have a product called Sync Switch that is a much more of a general purpose remote control automation device that you can use to make plans with. So those are the 5 reasons. LoRa is how we fix these problems, how we fix the problem, and I hope this has been helpful. If you like it, please comment a bit. I'll appreciate it. Thank you very much.
Wireless Wednesdays coming to you every week.